Next, let us discuss the concept on induced electric field due to time varying magnetic field. Let us consider the radio waves, microwaves, infrared, even the visible light, ultraviolet rays, X-rays, gamma rays. All these rays have wider applications in our day-to-day life, and all these rays are nothing but an electromagnetic waves. Then what are electromagnetic waves? The electromagnetic waves are the oscillating electric and magnetic fields which are propagating in particular direction. Here in electromagnetic waves, the change in electric field is producing the magnetic field, and the change in magnetic field again produces the electric field. Like this, the changing electric field and magnetic field produces one of them, and they propagate in the space. And these electromagnetic waves, even they can travel in vacuum also. Then from this we can understand that the electric field is not produced by the charges, because the electromagnetic waves are even traveling in the vacuum. Then if there is no charges to produce the electric field, then who is producing the electric field here? Surely the electric field is produced by the time varying magnetic field. So whenever the time varying magnetic field produces an electric field, that electric field we call it as induced electric field. So this electric field is not similar to that of what electric field is produced by the charges. Is it clear? What is the difference between the normal electric field that is created by the charges and an induced electric field? The induced electric field is created by time varying magnetic field, and it is not similar to the electric field which was created by the charges. Let us discuss in detail further. If you consider a closed loop like this and a bar magnet which is taken here, north pole and south pole, and the magnetic field lines will passes through the loop like this. Let us take this closed loop or closed wire stationary, and this is not going to move anywhere. Instead, I am going to take the bar magnet, and if it is taken closer to the coil and away from the coil, in that way I am trying to change the magnetic flux associated with the coil. So at every instant of time when the bar magnet moves, the magnetic field associated with the coil changes, so that here the magnetic field associated with the coil is not same, and instead the magnetic field is going to be the function of time if the bar magnet is moving towards and it is moving away from the coil continuously. And according to the Faraday law, we know that whenever there is a change in magnetic flux associated with the coil, it induces an EMF in the coil, and the magnitude of EMF is given by rate of change of magnetic flux associated with the coil. So the magnitude of EMF is proportional to the rate of change of magnetic flux associated with the coil, and if I remove the proportional, then I will be writing like this: minus d phi b by dt, and this negative signs is because of the Lenz's law. And if we introduce the magnetic flux as BA, where A is the area of the coil and B is the magnetic field which is present in the coil at a given instant of time, then I can write that this is, if the area of the coil maintained constant, then minus A dB by dt. This is the value of induced EMF whenever there is a change in magnetic field, right? And this Lenz's law tells that the induced EMF will causes the current to flow either in clockwise or in anti-clockwise direction in the loop in such a way that it opposes the change in magnetic flux that produced in the coil. For example, if suppose I take A bar magnet is taken closer to the coil. Now the incoming magnetic field lines into the loop are increasing. So when the incoming magnetic field lines are increasing, then this induced EMF will create a current in such a way that they will try to oppose the increasing incoming magnetic field. How I can oppose? If I try to produce the current in this direction, so that the current produced in this direction, and the current itself is producing the magnetic field opposite to the direction of increasing incoming magnetic field, and this is how the current is produced, and this is given by Lenz's law. Next, a question comes. A current means what? It is the rate of flow of charges. Suppose if this coil has a resistance R, then the current flowing through this coil is given by the EMF divided by R, and here this current is nothing but the rate of flow of charges, that is dq, that I can write it as dq by dt is ER, then dq is equal to E by R into dt. Again a question comes, everything is okay, the rate of flow of charges is causing the current, but how the charges moves? Who is pushing the charge to move from one place to another place? Is there any force that is acting on the charge so that the charge moves inside the wire? The answer is electric force. How an electric force is produced? Because there is a presence of electric field is creating an electric force on the charges, and that force acting on the charges is given by F is equal to QE. So if there is no presence of electric field, then there is no possibility of getting a force, and that force is making the charge to move, and because of that movement of charges we are getting the current. Again one more problem comes, is that the force is an electric force. Why can't it be magnetic force? See my dear children, the magnetic force is created only if the charge itself is moving in the magnetic field. For example, if I consider the constant or uniform magnetic field which is passing perpendicular to the plane of paper, and this magnetic field is constant, and if I take a rod like this, and this is having a length L which is moving with the velocity v, if the rod moves with the velocity v, the charges inside the rod also moving in the same direction. Now because the charge moves perpendicular to the magnetic field, it will experience the magnetic force that is called as Q into V cross B. Now because of that, the positive charge will experience the upward force and they will start accumulate here, and the negative charge will experience a downward magnetic force and they starts to accumulate here. Because of that, the charges has moved. Here the charge is moving, so magnetic force is created, so the charges are distributed. But here, does the charge moves by itself? No. The charges are remain stationary in the wire, and because there is a change in magnetic field, it creates an induced EMF. That induced EMF is creating an induced electric field, and that induced electric field is creating a force, and because of that force the charge is moving in the coil wire. Even if there is no coil, there will be a presence of what? Induced electric field. Now inside the coil, let me say, if the current moves in this direction, then the force is also acting in the same direction of current. Then what is the direction of electric field? If the force is in the direction, then the electric field also will be in the same direction. Now you can see that the electric field is throughout the wire and they are forming a closed loop. And if I take any point in that closed loop, the direction of electric field is given by drawing the tangential line at that point. And this electric field line is forming a closed loop inside the time varying magnetic field. Is it clear, children? let us try to find out what are the differences between this electric field, that is static electric field, and induced electric field. So static electric field and induced electric field. This static electric field are produced by charges, are produced by static charges. But this induced electric field are not produced by the static charges. Instead, it is produced by time varying magnetic field. Next, this electric field produced by the static charges, they starts from positive charge like this, and they will try to terminate at the negative charge like this. So it means this static electric field will never form a closed loop. But if you look at the case of induced electric field, they always form a closed loop like this. So at any point, if you try to consider the electric field, and that is given by the tangential line that is drawn at that point. So here the induced electric field will always form a closed loop. And here the static electric field, if I consider the uniform electric field in this direction, and inside the uniform electric field, if I try to take a charge and I am trying to move in the direction of electric field and perpendicular to the direction of electric field, opposite to the direction of electric field, and again coming back to the same place. Now this is what the movement of charges. Now if you move the charges around the closed loop, here if you calculate the work done in moving the charge around the closed loop will be 0. Then if the work done in moving the charge around the closed loop is 0 inside the static electric field, then this electric field is given as conservative field. But if you move the charge inside the induced electric field, will the work done be 0 or not? To understand that one, let us take a wire and it has some thickness like this. If suppose there is a time varying magnetic field, and here the magnetic field is varying with respect to time, if there is a time varying magnetic field, then around the wire the charges moves because of the presence of electric field, and that electric field at every point, it is given by the tangential line at that point, right? Now if the charges moves around the wire, you can see that the displacement of the charge, of any charge, the displacement also given by a tangential line. Now if you try to find out the work done is given as integral over the closed loop E vector dot ds vector. Here the E vector I can write it as F vector dot ds vector. What is F vector? That we have already found here. Then I can write that work done is equal to integral over the closed loop q E vector dot ds vector, and see that E vector and ds vector in same direction, so cos 0 degrees 1, then W is equal to integral over the closed loop QE ds. Then what is integral of ds? And that is given by the circumference. Here the circumference, let me take it as L, then I can write W is equal to QEL. So what does it says? The work done in moving the charge around the closed loop is not 0. Then we can tell that this is not a conservative field, this is non-conservative field. And from this work done, we can change this EMF equation also, because the EMF is given by work done in moving the charge, which is equal to minus a dB by dt. If I introduce this value here, then Q and Q will get cancelled, then EL is equal to minus a dB by dt. Then I can write E is equal to minus A by L dP by dt. Here L is nothing but the circumference. So this is a formula that can be given as an induced electric field. With this, I stop the discussion of what is induced electric field, and based on this we can even try to find out many numerical problems, and using this kind of approach we can solve that numerical problem also. Thank you.